Section 3.1. Today we're going to learn about exponential functions and their graphs, along with the properties of exponents. It would be to your advantage to take notes. Okay, so now we're going to do properties of an exponent. For the product property, if the two numbers that are being multiplied both have exponents, the exponents would be added together. For example, x to the third times x squared would become x to the fifth. Now for the quotient property, if both the numbers in the numerator and the denominator have an exponent, the exponents are subtracted. For example, y to the seventh over y to the third would become y7 minus 3, which would be y to the fourth. For the negative exponent property, if there is a negative in the exponent, you would move the number to the denominator and it would become positive and you would put it over 1. We're going to use the example of x minus 3, which would become 1 over x to the third.
For the next property, we have the zero exponent property, and it's any number to the 0 power is always 1. So you could have 8 to the 0 power, and you just have to know that it's going to equal 1. The next we have power of a product, which is two numbers to the same exponent. So you could have 3 times 4 to the third exponent, and then you just have to know to distribute the exponent. So it's 3 to the third power and 4 to the third power. For the next, we have power of a quotient, which is a fraction with an exponent. So you have to distribute the exponent to both the numerator and the denominator. So you could have 4 over 5 all to the second power, and it's 4 to the second to 5 to the second power. Then you have power of a power, and it's two exponents. One is in the parentheses, so you just have to know that you have to multiply both exponents. So you could have x to the fifth power all over to the second power, which just equals x 5 times 2, which equals x to the 10th. Okay. Definition of an exponential function is f of x equals a to the x, where a has to be greater than 0 and a cannot equal 1, and x is any real number.
For example number 1, we have f of x equals 3.4 to the x power, and in this case x equals 6.8. In your calculator you would type 6.4 raised to the 6.8 power, and your answer should come out to 4,112.033.
Okay, for example number 2, we have g of x equals 5 to the x power. And for this problem, you actually have to make an x and y table. And you can plug in any number you want. So we'll just use simple numbers like -2, -1, 0, 1, and 2. So you have to plug in each exponent. So for the first number, you have f to the power of -2. And the way you do this, you use one of the properties, and it's 1 over 5 to the second power, which just equals 1 over 25. So for this, it's 1 over 25. And then you keep going with the rest x values, and it's 5 to the -1 equals 1 over 5 to the power of 1, which equals 1 over 5. 5 to the power of 0 is always 1. 5 to the 1 power is just 5. And 5 to the power of 2 equals 25. So now that you have your x and y table, you just need to graph each number. So you could just be 1, 2. And since this is fractions, you could just go over 5. So this is just 5, 10, 15, 20. And you're just graphing it. So the negative 2 is 1 over 25. So you just estimate it and just plot some points there. And 0 is to the 1, and 1 would be somewhere here. 1 is 5, and 2 is 25. And that's what your graph should look like. Okay, so your Horus asymptote should be at y equals 0, and that is because there's no transformations telling you to move y anywhere else. And you would say that your graph is increasing.
For example number 3, we have f of x equals 5 to the negative x. So for this one, you have to make an xy table as well. And we're going to use the same numbers as last time, which are negative 2, negative 1, 0, 1, and 2. For this one, when you raise 5 to the negative 2 power, since this is already negative, the negatives cancel out, so your answer would just be 25. And also for negative 1. And as we learned for the zero product property, any number raised to the zero product is always 1. And for the other ones, it would also be the same way we did in the last problem, so negative 1, and this would just convert into and the same with negative 2. Now for this one, we also have to graph it. And now we just plot the points. So negative 2 would go up to 25. And then negative 1 would go up to 5. And then 0 we have at 1. And then since you can't really get an accurate measurement of this one, you kind of just have to estimate. And your graph should look something like this. For this one, your y is also going to be at 0, and this graph would be considered decreasing.
For example number 4, we have f of x equals 4x minus 2, and the minus 2 is just a transformation to your graph. So the way you're going to start is just an x and y table. We're going to use the same numbers, which is negative 2, negative 1, 0, 1, and 2. So you start 4 to the negative second. You have to move it to the denominator, which is 1. 4 to the second power, and is 1 over 16. And you keep going the same way. You move it to the denominator, is 4 to the first power, and it's just 1 over 4. 4 to the 0 power is always 1. 4 to the first power is 4, and 4 to the second power is 16. So all you do is plot the points. And you have 1, 2, 3. I'm going to use my graph by 4s. Okay, so first number is negative 2 of 1 over 16. So negative 2, and you're just estimating where 1 over 16 would be. And then negative 1 is 1 over 4. 0 is at 1. 1 is at 4. And 2 is up at 16. And this graph would actually be wrong because you have this transformation here. So you want to move down your whole graph down 2. And this would be where your asymptote would be at. Would be at negative 2. So you just move down all your graph.
So now we're going to be moving on to continuous and quarterly interest, and for the quarterly formula, it's A equals P times 1 plus R over N to the NT power. P is the principal, which in this case would be 6,000. R is the annual rate of interest, which in this case it would be 6%. N is the frequency of compounding, which you have 4 years. And T is the time in years, which would also be 4 years. Okay, and A is the total interest, so we're looking for that. Okay, so now we're going to start the problem. The problem is a total of $6,000 is invested at an annual interest rate of 6%. Find the balance after 4 years if the interest is compounded quarterly and continuously. So we're going to start setting it up. So you're looking for A. It would be 6,000 times 1 plus 0.06 over 4 times 4. Okay. Listen to the calculator. Your answer should approximately be about 7,613.91. So now we're going to be doing the one for continuously compounded, and here we are still looking for A, but the formula has changed. And E is not a variable, it is just a button on your calculator. So you would plug it in like this. Okay. Wait. When you plug this into your calculator, you should get the approximate answer of 7,627.44.